Hello everybody. In the last class we looked at ASM chart and given a problem statement we have seen how we can get a ASM chart for that particular problem statement, and we took up vending machine which has got two inputs as an example. We also saw the sequence detector example, right? So in today's class we shall look at circuit realization using ASM chart, and after that we shall look at a decoder-OR based combinatorial circuit realization process, okay. And finally we shall move to state minimization, and we shall look at one method called row elimination method, okay. So for ASM chart based circuit realization, so the problem that we had taken up in the previous class, we continue with that, okay. So that the vending machine problem where rupees 5 and rupees 10 coin can only be deposited and the product is priced rupees 15. There is a coin sensing mechanism where if the sensor I is 0, that means no coin is deposited. Whenever a coin is deposited, it becomes 1, and there is another sensor, if it is 0, when coin is deposited, it is rupees 5 that has been deposited. If it is 1, rupees 10 has been deposited. And the output, there were two outputs, X and Y. X delivers the product. When X is equal to 1, product is delivered, otherwise X remains 0. And Y is equal to 1, rupees 5 is returned, because by any chance it goes to rupees 20, that means the total money that has been deposited into the vending machine, say rupees 10, then rupees 10, or rupees 5, then rupees 10, okay, whatever be the sequence, then a rupees 5 coin is returned to the customer, okay. So this is the problem statement with which we worked, and we arrived at this state transition diagram, okay. We did part by part analysis every state, and this was the state transition diagram, okay. So up to this we had done in the previous class, right. Now to implement this particular circuit, we need to first do a state assignment, okay. So states were defined as A, B and C, we have already noted. So we considered that we know 3 states means 2 flip-flops will be required. So 2 flip-flops, we name it B and A, capital B and capital A, okay, and corresponding states are 0, 0 for A, for B it is 0, 1, and for C it is 1, 0. So next important task is to move to state table from ASM chart, okay. So what we shall look into in that part, okay. So for every state that has been defined, so B and A n, so that is when it is 0, 0, it is state A, okay. So state A, there are 4 possibilities at the input side. I is A, 0, 0, 0, 1, 1, 0 and 1, 1, okay. So of course I is equal to 0, then J is 0, 1, it is, doesn't matter because no coin has been deposited, that is the case, okay. So 0 cross, that is the way we had defined it over here, okay, over here. Each of these cases, what is the next state, right? So for I is equal to 0, the next state is state A only, that is 0, 0. So that is what you see over here as 0, 0, 0 and 0. Is it fine? And if it is 0, 0 current state, okay, that is state A, I is equal to 1, that means the coin has been deposited, right, and J is equal to 0, that means rupees 5. So it goes to state B. State B is defined as 0, 1, rupees 5 accumulated, so that is your 0, 1. And 0, 0, and then the input is 1, 1, that means rupees 10 has been deposited. So in the ASM chart we can see that it is going to state C, right. So it is going to 1, 0. Is it fine? So from the ASM chart we can find out for what combination of the input I and J, from current state we go to a specific next state. Is it clear? Right? So that is the ASM chart to state table mapping. Once it is done, rest of the thing is as we had done for sequential logic design circuit. Okay. So next is 0 1. 0 1 is your state B, that is the way we have assigned state, right. So these two cases, I is equal to 0, so it will remain at state B on state 0 1 only, state small b only, right. And when it is 1 0, that means rupees 5 has been deposited, rupees 5 and rupees 5 it will go to rupees 10 state, that is C, that is 1 0. You can see over here from the ASM chart, we can figure it out that the path leads to state C, right. And from 0 1, if it is receiving a 1 1, okay, that means rupees 5 and rupees 10. So if we go back, so in the ASM chart we can see this is state B, right. So this is 1 and this is 1, right. What does it do? It delivers a product x is equal to 1 and it goes to state A, right. Okay. So we can write when it is at 0 1 and it is at 1 1, it is going to 0 1, 0 0, that is state A. Is it fine? Next, if it is 1 0, that means state C, right. 0 0, it will remain at state C only. 1 0, it is going to that means rupees 5 has been obtained, so it is going to state A and delivering only the product. 1 1, that means rupees 10 and another rupees 10 has been received, it is going to state A, initial state A. You have seen that in the ASM chart, and delivering the product and delivering also returning a rupees 5 coin. Is it fine? Okay. So this we can map from ASM chart to state table. Once that is done, rest of the thing is as we have done in the earlier classes for sequential logic design circuit. Okay. So mostly we have used JK flip-flop. So for a change, let us use D flip-flop, and it has certain other significance that we shall see later. Okay. So if you use D flip-flop, then the excitation table is very simple, right. Whatever is at the input of the flip-flop that goes to the output, so whatever is the next state, so that will be the input value of the flip-flop, isn't it. So for which whatever is the input values, what you see over here, next state values, so those are the dB values, right. Similarly, whatever are the next state values for an plus 1, so those are the values for dn. Is it fine? Okay. So with that, we go to what will be the next step? To get the design equations. So these input equations, right. So with these inputs, this way it has been written 0 0 0 1, 0 0 1 0, 1 1 0 0, this is for dB. Okay. So you can see that is the case 0 0 0 1, okay, 0 0 1 0, then 1 1 and 0 0, and then the rest are don't care. Okay. The rest are don't care. Okay, because 1 1 is not there, fine. So the rest are don't care, fine. So then if you form the groups, so these are the two groups you can see, and this is another group. So these are the 4 variables that are there, okay, by which you get this equation. Similarly for the other case. Is it okay? So this is one group this is for DA, a group of 4 members, and this is another group which is given by this one, okay. I, J bar, B n bar, N bar. Similarly for the rest of the cases. This part you know very well, isn't it? Okay. So this is the equation for the flip-flop inputs, and then corresponding equation for what is it called? These outputs, right? Since it is Milli model, so output equation considers the input as well, isn't it? So that is I and J. Had it been Moore model, it would have been solely generated from the flip-flop output. So these I and J would not have been considered. Okay. right. So, that is why you see that all these two inputs as well as the states are considered over here. So, accordingly this is the equation, and you have got another equation for y over here. Okay. So, x and y. So, we are directly mapping it from state table to the design equation following the similar process that we have followed before. Okay. So, once we get these equations, okay, so these are the equations that we have obtained. So, next is putting them into the circuit, right, that we all know how it is to be done. So, if you just take one of them as the example, so this is your A flip flop, right. So, DA, if we look at the DA, right, so this is I and this is I bar, right, and then this is your A, right. So, this A is coming back over here and this is I bar. So, I bar A n, right, and this is I j bar B n bar N bar. So, this is the 4 input AND gate, right, which is taking those necessary inputs, okay, and then you have got a OR, right. So, this is by which you are getting the DA. Similarly, for the others clock is common, right, and output is generated in this manner. Is it fine? Okay. So, you understand how to realize convert the circuit, just we follow the same steps. Okay. Now, to note that compared to JK flip flop based circuit looks a little bit more complicated, isn't it? Because it provided I mean at least the commutatorial circuit part, okay, because it has got less number of don't cares and other things. So, that way the equations that you get has got more variables, more literals present in the equation. Okay. So, that is what you see over here. Okay. Now, that gives us one opportunity to look at the other options that could be there for realizing this circuit, and one such option could be when we are using D flip flop, okay, knowing fully well that the next state is the input to the flip flop, right. Then we can use an arrangement, okay, the way we had done, if you remember the commutatorial circuit, the decoder-OR based multiple output generation scheme. So, we can employ that for the commutatorial part of the circuit. Okay. It will not be most simplified, but from hardware point of view it will be easier to get. So, for that we need what? So, this is a 4 to 16 decoder. Okay. So, this is a 4 to 16 decoder, right. So, Bn, An, I, J, these are the 4 inputs, and 0 0 0 0 0 1 0 0 1 0 up to 1 1 1 1, these are the corresponding outputs. So, depending on the combination present, if 0 0 0 0 is present, so this will be high, all rest of the things will be 0. Okay. If instead 0 0 0 1 is present, this will be high, okay, and rest all the outputs will be 0. This is how a decoder works. Is it fine? We remember that, okay. So, we use that concept, right, and we can see the state table that we have got, okay. We can directly convert, okay, to a decoder-OR based commutatorial circuit representation. Okay. How? So, the D flip flop that we shall be using, 2 D flip flop that are there. So, this is the corresponding input, right, and if this is your 0 Bn An I J, okay. So, this is your 0 0 0 0, right. For that dB is 0, 0 0 0 1 dB is 0, 0 0 1 0 dB is 0, and 0 0 1 1 dB is 1. Okay. That is what you can see. Similarly, for 0 1 0 1 dB is 0. This way you continue. When 0 1 1 0, for this particular case, this is 1, right. Similarly, for 1 0 0 0, this is 1, 1 0 0 1, this is 1, right. So, what you can see for this particular input combination, if we write dB as a function of Bn, An, I and j and the 16 minterms that are getting generated, okay. So, these are, this is 0 0 1 1, so 3, then this is 6, right, and then this is 8 and this is 9. So, if you just sum them up, right, we will get the value of dB, isn't it. So, this decoder is generating all the minterms, right, and we need to have a 4 input OR gate over here in the decoder OR gate combination. So, this will be the function this sigma m 3689, which is basically the function, the design equation for dB. Similarly, for dA, if you just look at it, it is 2 4 5, okay. So, you can have this another OR gate, so that is why I have given dot dot dot, and so, and from that you can get the corresponding input for dA. So, that you feed to the flip flops. So, you will be feeding that to D flip flop over here. So, similarly over here you will be feeding to that D flip flop over here. So, this is your D, this is your D, this is your corresponding B and this is your corresponding A, and this B will be fed here and DA will be fed there. Is it fine? Right? So, this is the way you can design the circuit. So, this is the commutatorial part of the circuit, the commutatorial part that you had seen which got designed, okay, by these design equations and is represented in this manner. This is minimized, but you have to use many gates, but this decoder comes in a compact IC, integrated circuit fabricated, so you can use those output and can make use of multiple OR gates. So, similarly X and Y you can generate from this decoder output also by appropriate this thing. Is it fine? Right. Now, we have seen this Milli model, mood model and state transition diagram, ASM chart, realization using standard simplification, following standard simplification, or by using this kind of arrangement where decoder can be used, okay, to generate the minterms. Now, we look at another aspect of this synchronous sequential circuit design, which is called state minimization. This is important because often from the problem statement, the state definitions that we are doing and then arriving at the state transition diagram or the corresponding say ASM chart, it could be so that we have actually considered more number of states than necessary, isn't it? If you remember the way we have defined the states in the sequence detection problem. So, A no bit has been detected properly, B one bit has been detected and so on and so forth. So, that is from the intuition, that is from our understanding of the problem statement we are doing it, right. Okay. Similarly, for vending machine problem we are looking at no money has been deposited, then rupees 5 has been deposited, rupees 10 has been deposited, these are different states. Okay. So, we made a logical argument of the case and defined those states, right. So, there may be more complex problem, more difficult to understand, right, and logically we may unfurl it and get those states, but it is not necessary that those states to begin with are the most minimized one, okay. Or we as an implementer, somebody gives us a state transition diagram, we have been asked to implement it, okay, we can look for whether there is any redundancy, and then if we can come up with a minimized state representation, that will help us in reducing cost, reducing time and many other things associated with it, okay. The time complexity of the design and many other aspects that will not be there. Is it fine? So, remember the minimized state transition diagram or state machine will be giving you same input output relationship without any difference. So, it will not alter the input output characteristics, but only the internal states that are required to generate the circuit, generate the corresponding output in reference to a particular sequence of input, that only is getting changed, that is only getting reduced. Okay. Is it fine? So, with this background, let us see an example and learn through that particular example how it is done. So, we shall take up one method today, and in the next class we will take up two more methods, two more popular methods. Okay. So, this is one state transition diagram, okay, that has been obtained from some source, right, and then we have a job to see it whether it can be minimized or not. So, we see that A, B, C, D, E, F 6 states are there, okay, and for that the first method that we shall employ is called row elimination method. So, before that we first understand that two states are considered equivalent, if they move to same or equivalent state for every input combination and also generate same output. Okay. So, that is when we shall consider two states are equivalent, okay, when they are moving to same state, okay, or equivalent state. So, that equivalence we have to see and generate same output. Okay. So, for that this state transition diagram we first move to a corresponding tabular form. Okay. So, this is the present state A, B, C, D, E, F, right. So, next state for input only one input is used, this is a Mealy model we can see. So, x is equal to 0 and x is equal to 1. Okay. So, the corresponding next state are for A, you can see for x is equal to 0 this is A, for x is equal to 1 this is B. Okay. What are the corresponding outputs? From A, if input is received is 0, output is 0, input received is 1, output is still 0. Okay. So, that is how we get the first row of this table. Similarly, B, we can see B, it is going to C and D, C and D, and in each time the output is 0 and 0. For C, it is going to E and F, output is 0, 0. For D, it is going to B over here and A over there, B over here, A over there. Going to B, output is 0, and going to A, output is 1. Fine. E, it is at E, it is C and D, C and D. That is what you can see, output is 0 in both the cases. For F, it is going to B and A, right, and output is 0 over here and 1 over there. Is it okay? So, this is the way to map it in a manner which is easier for us to apply the equivalence relationship and investigate, examine redundancy. Fine. Right. So, once we have put there and we employ that particular concept of equivalence, we can see B and C, right. So, next state is C and D, next state is C and D. Output is 0, 0, 0, 0. So, we can say B and E are equivalent, B and are equivalent, and we can eliminate one of them. So, that is called one row eliminated. So, the larger, the one that comes in later in the order. So, E has been removed and B has been retained. Okay. And in this table, in this representation, wherever a reference of E was there, for example, here, since B and E are equivalent, we are replacing it with B. Is it fine? So, this is what we have done. One row has been eliminated, right, and the one that has been eliminated with the equivalent one, reference to that particular state is made with the one that is eliminating, that is B over here. Okay. So, now we can further investigate and see that D and F, next state is B and A, and output is 0 and 1, 0, 1, 1 in each of these cases. It is matching for the corresponding input. So, you can say D and F are equivalent. Okay. So, we shall retain one of them and remove one of them. Okay. So, F will be removed because it comes later in the order. So, that is what we shall do. So, move to the next slide. So, that has been done, right. So, before that, wherever the reference of F was there, so here was the reference of F, so F has to be removed with D. So, F has been removed with D. You can see that F has been removed with D. Okay. After that, if you further examine, as such, there is no such two rows where exactly some such thing is there. I mean, the next state and output are exactly the same. But one thing you can see that B, state B, it goes to C and D 0, 0. C, it goes to B and D 0, 0. So, these two D matches, 0, 0 matches, 0, 0 matches. So, only where in this place C and B are not matching. So, had they matched, so if C and B were equivalent, then we can say that this B and C are equivalent, B and C at the inputs, I mean the current present state side. Okay. So, next state C and B are equivalent if present state B and C are equivalent. Okay. So, this is from tautology, we can say B and C will be equivalent because the necessary requirement is C and B are equivalent, and we are looking for equivalence, okay, redundancy and minimizing it to the extent possible. So, we retain one of them and eliminate the other. So, it becomes 3 rows now, C is removed, okay, and wherever reference of C was there, we are replacing that with B, right. So, here we are replacing that with B, and if we examine, we can see that no further elimination is possible. So, now we have got 3 states A, B and D, A, B and D. So, from 6 states we have come down to 3 states by this method, and now if you convert it to the state transition diagram if so required. Okay. So, you can see that this is A, 0, it is remaining at 0 and output is 0. So, this is the 1. For x is equal to 1, B and output is 0, it is going to be B, output is 0. Then B at 0, it is remaining at 0, okay, output is 0. 1, output is 0 and going to D, 1, output is 0 and going to D. At D, okay, it is for x is equal to 0, it is going to B and output is 0, going to B, output is 0, and for 1, it is going to A and output is 1. So, it is going to A and output is 1, right. So, this is the reduced state transition diagram, and you can give any inputs sequence, random sequence of x, say 1, 0, 0, 0, 0, 1, etc., right, and you can examine if the current state is A and next state is, what will be the next state? It will be, the next state will be B, and what will be the corresponding output? It will be the 0, right. Then 0, next state will be B, output will be 0. So, that way you go on doing it, you will find for the previous one and the current one or any random sequence that you have taken. So, these output will remain the same, only the next state values will be different, okay, because of the equivalence that are there. Okay. So, this input output relationship does not alter because of this, and of course, you will be realizing with less number of flip flops, okay, and as I said, less complexity, design complexity and many other things, hardware cost, okay, and so that is the advantage of state minimization. More methods, other methods we shall see in the next class. So, to conclude, circuit realization using ASM chart is similar to state transition diagram method. Okay. It follows steps like state assignment, state table formation, design equation through simplification method like Karnaugh map, and finally translating design equations to circuit. And for large complex circuit, we can have seen that it may make more sense to convert the state table to a decoder-OR based realization directly from the state table itself, okay, and the combinatorial part of the circuit. And state reduction technique is useful for removing redundant states, and two states can be considered equivalent if they move to same or equivalent state for every input combination and also generate same output. So, both are required, and in row elimination method redundancy is removed sequentially by eliminating rows after testing equivalence. Okay. Thank you.